Imagine a world where the tiniest building blocks of matter, invisible to the naked eye, hold the secrets of the universe. Welcome to the Atomic Odyssey, where we embark on a voyage through time to witness the remarkable evolution of our understanding of atoms. Long ago, in the heart of ancient Greece, lived a curious philosopher named Democritus. As he examined cheese and bread, he wondered, could matter be endlessly divided? Democritus envisioned tiny, indivisible particles he called atomos, the building blocks of everything around us. The torch of curiosity passed through the ages, igniting the fire of alchemists' experiments. Yet it was merely a prelude to the scientific renaissance. John Dalton, a brilliant chemist. With his atomic theory, he painted a new canvas of understanding, each element composed of unique atoms combined in simple ratios to form compounds. Though his theory was groundbreaking, it had its limitations. Dalton's assumption of indivisible atoms would soon face the winds of change. Apparently, it was the reason for its rejection. But then, a spark of electrifying discovery. J.J. Thomson, with his cathode ray experiment, introduced electrons, the tiny, negatively charged particles, shattering the idea of the indivisible atom. While the majority adopted Thomson's model, it was rapidly rejected as it failed to realize atomic stability because it did not describe how the negative charge, electrons, is contained inside the positive sphere. Rutherford proposed a planetary model of the atom. In this model, the atom consists of a tiny but very concentrated region of positively charged nucleus, surrounded by orbiting electrons. Rutherford's atomic model failed to explain the stability of electrons in a circular path. That's one of the reasons why his model was rejected. Danish physicist Niels Bohr proposed a new model of the atom in 1915. Bohr proposed that electrons do not radiate energy as they orbit the nucleus, but exist in states of constant energy that he called stationary states. This means that the electrons orbit at fixed distances from the nucleus. This is also referred to as the planetary model of the atom. As a result of quantum mechanics, the motion of the electrons around the nucleus cannot be exactly predicted. It is impossible to pinpoint the velocity and position of an electron at any point in time. The shells in which these electrons orbit are therefore not simple lines but rather diffuse, less defined clouds. Chief among the many investigators of how atoms really act was Austrian physicist Erwin Schrödinger. In 1926, Schrödinger proposed that rather than the electrons moving in fixed orbits or shells, the electrons behave as waves. This seems a little weird, but you probably already recall that light can behave as both a wave and a particle, what's known as a wave-particle duality, and it turns out electrons can too. These clouds are clouds of probability. Though we don't know exactly where the electrons are, we know they're likely to be found in given regions of space. These regions of space are referred to as electron orbitals. It's perhaps understandable why high school chemistry lessons don't lead in straight with this model, though it's the accepted model today because it takes a little more time to get your head around. Schrödinger's model is still widely accepted as the most accurate model of the atom.